So now how do we work on a normal distribution that is no longer a standard normal distribution? And in other words, I call this type of normal distribution some general normal distribution. Meaning, we will no longer use the random variable z, but instead we are using the random variable x. Some random variable x to represent our population data, a continuous random variable. And symbolically, our continuous random variable is distributed normally. That's what the n is for. But now our mean and standard deviation no longer at 0 and 1. We're now at some mean, given mean, and some standard deviation. So remind yourself, once again, mean is given, as well as sigma, the population standard deviation, is also given. And our bell curve is going to look like this. We have a horizontal axis having all different values of our random variable x. And our bell curve is a nice PDC with a bell-shaped curve. And the mean value is, once again, remind yourself, exactly in the middle. And we won't trivially see how the standard deviation being displayed in this graph. However, we can always note the given value of the sigma of the standard deviation somewhere near our curve. All right, so now that we are no longer on a standard normal distribution bell curve, but even though we're no longer on the standard normal distribution bell curve, this general normal distribution bell curve that we're looking at here still has a very close relationship with the standard normal distribution that we have studied carefully. But before we actually investigate what that close connection between this general normal distribution with the standard normal distribution, I need to remind anyone viewing this video that so a bell curve in the end doesn't matter if it is a general normal distribution or a standard normal distribution. A bell curve, the curve itself is a PDC. And so inside the curve, the area completely shaded inside the curve represents the total amount of data that's being inside. And so, and the horizontal line here represents the line where we can place all values of our random variable, in this case x, from low to high, from the left to the right. And so what I need to remind everybody or anyone viewing this video is that, let's say now we have a value of our random variable x being a, and we have another value of our random variable x being b. And let's say for a being less than b, here we have an interval from a to b. And so the probability that on this bell curve, the random variable takes value either anywhere between a and b, or including the inequality, we can have a statement as following. Find the probability that our random variable capital letter X here takes value anywhere from a to b. And so either one of these two probability questions is graphically understood as the area shaded inside the interval here on the bell curve and between the interval from a to b. But this is just a property that's always true for any probability density curve, any PDC existing out there. And so now I am going to bring up an example to unlock what that close connection between any general normal distribution and a standard normal distribution is. So in our example, let's say we are given a standard normal distribution, a bell curve that's having mean at 3 and standard deviation 0.25, for example. So according to this description, what we're looking at here is that, and so notice how the center, the mean value is no longer 0 and the standard deviation is no longer 1. This bell curve, this normal distribution we're having here is no longer the standard normal distribution as I have described earlier. And so now immediately seeing this notation n3, 0.25, I am going to immediately draw an empty bell curve and getting it ready for action. So 3 now is at the center, and our sigma value, instead of being directly seen through the picture, we can just simply label that somewhere along with the picture itself, and any value found on this line is a value of our random variable capital X. Alright, so now right from this given information, let's say the actual question I'm bringing up in our example here is to find the probability that our random variable takes value anywhere from 2, how about 2.9 to 3.15. And so now looking at this picture, this is how I see. We don't need to worry about precisely how far 2.9 is on this bell curve away from the 3, but what makes sense immediately is that 2.9 has to be somewhere to the left. So I can just draw it somewhere so that we can have enough space for drawing. So 2.9 is here, and 3.15, how far that is, somewhere, it shouldn't matter, but what makes sense immediately is it should be somewhere to the right hand side. So again, I'm saying 3.15 should make sense immediately to be somewhere to the right hand side of our mean at the middle. And at this point, it's a better idea that I am going to write my mean value in red ink to make clear that it's a center on this bell curve. And so this probability having equality included or without equality included in the end is understood. The answer, the outcome of this problem is understood as the shaded area inside the bell curve and between the two values indicated here. And so now we have graphically represented our probability here on the bell curve. And so now to find, but keep in mind again, before I'm showing the real methods for how to find area on a bell curve, but no longer on the standard normal distribution. This is now we are finding area on the general normal distribution. So before I introduce the actual technique and point out how closely relate this is to the standard normal distribution, then I need to remind anyone a quick little math problem. 2.9 being our lower end of the given interval, I am going to subtract 3. This is the center of the bell curve, or another way of calling that, it's the mean value. And I'm dividing that difference by 0.25. So take it slow and understand clearly where these two values come from. And you will understand better about what this setup is all about. But so calculation comes out to be negative 0.4. And so now as I'm slowly going through this calculation, anyone viewing the video must now recall that this is the setup to calculate the z-score. And now specifically, this calculation here landing into negative 0.4 is the z-score for 2.9. And so now, similarly, I am going to be doing the same for our upper end of the interval. So again, I'm not directly pointing out what's the connection between the general normal distribution we're currently having here with the standard normal distribution yet. But what I'm pointing out right now is that the value we're having as our low end of the interval has provided us a z-score. And so the same way, I am going to find the z-score correspondingly for this higher value or upper value of our interval. So here it goes again. The math comes out to be 3.15 as our value of the upper end of the interval, minus 3, the center on the bell curve or the mean value of the data, and we're dividing that by 0.25. Calculation comes out to be positive 0.6. And again, as I'm going slowly through the progress of getting this value 0.6 right here, anyone viewing this video must now realize that this setup right here of the calculation is the calculation for a z-score. And now specifically, this is the z-score for our upper value, 3.15. And so now it is good to, it's not exactly required, but it's always a good idea to write down the corresponding z-score right underneath on the bell curve picture over here. I'm going to write down the corresponding z-score for each of these values right underneath them. So 2.9 has an equivalent z-score being negative 0.4, and 3.15 has a corresponding z-score being 0.6. And so now think about that. This center over here, this center right here stays right on mean, so it has a corresponding z-score being 0 as well. So these two labels are not a requirement, but it's always beneficial to indicate them right underneath the actual value of our interval, right on any general normal distribution. But so now here's the real connection that between any general normal distribution with the standard normal distribution that we have learned right here. My argument now is that the probability we are currently finding on this bell curve, finding the probability where 2.9, our random variable x is anywhere from 2.9 to 3.15, this probability or this shaded area is exactly the same as the probability that on the standard normal distribution we're finding a z-score taking value anywhere from negative 0.4 to positive 0.6. That is the connection we have found between any general normal distribution and the standard normal distribution. Now, before I really proceed any further, then I also need to emphasize, unless being specified otherwise, z-scores are usually being calculated into 2 decimal places, and in our cases here, the z-scores themselves already in 1 decimal. But so, as I said, unless any instructor of yours or myself indicated, specified or specify otherwise, we're gonna by default keep these z-scores to the most 2 decimal places. But so now back to what we are doing. So finding this area or finding an answer to this probability question is exactly the same as finding the answer to this probability. So now imagine that we are on the standard, and the whole point now is that once we're putting ourselves back on the standard normal distribution, and now we can feel free to draw the standard normal distribution where the random variable now is z the center here of the bell curve is 0, and with sigma equals 1. Negative 0.4 is somewhere to the left, and positive 0.6 is somewhere to the right hand side. And the shading between these two z-scores are here produce an area for us. But so in what I am trying to explain, then these two areas, either the area on the general normal distribution or the area on the standard normal distribution, these two areas will be equal amount. And so now in that case, we have all the tools we need in order to calculate this area. I am going to start calling up my normal CDF command. So on my calculator screen here, on my standard TI 83 or 84 calculator, I am going to retrieve the normal CDF command. So second variables, and I'm going to scroll down to option number 2. I am going to hit enter. And so now for lower end, I am going to enter my lower z-score. So negative 0.4. I'm going to hit enter to navigate to the next line. The upper z-score we're looking at in our problem is a positive 0.6. So now I'm going to enter 0.6. And I am going to leave these two values defaulted to be at mu for 0 and sigma for 1, or 0 for mu and 1 for sigma. So that means I am going to hit enter a few more times to skip, and then now I am going to start executing that command. So again, I need to also remind anyone that using an older version of the TI 84 or the TI 83 calculator, then your command there, when you're actually executing it, then it will be completely syntax based. So you must enter the lower end first, which is a negative 0.4 in this case, and then put a comma, and we're gonna put the upper end after that, and a comma again, and we're gonna default these two values at 0 and 1. And so at this point, we are ready to really execute the normal CDF command to find out what our final answer is. And so back on my calculator, hitting enter, we're ending up with a 0.38116866325 and a lot longer. So that means this answer here, the answer to our probability problem, now has been found. The answer now is 0.3812. And as I have said back in our lectures about the standard normal distribution, unless being specified otherwise, final answer for a probability on a normal distribution bell curve will normally be rounded to 4 decimal places. So here, rounding to 4 decimal places, we are at 0.3812. And that is our final answer. And if this answer is required to be expressed in percentages, then this is about the same as 38.12% of area on the bell curve. And so now, what is the meaning of this value over here? These two values, it is actually one value, but either in decimal expression or in percentage, this value here represents that either we're on the general normal distribution or we are on the standard normal distribution. This value indicates that there is about 38.12% of the data on this general normal distribution bell curve center at 3 with sigma 0.25 being anywhere from 2.9 to 3.15. But that area is also exactly the same as if we were on that standard normal distribution. And this is exactly the area between anywhere from negative 0.4 to 0.6. Now, before we completely close down this quick little example and make a generalization, I need to also point out, I need to admit another truth. For public viewers out there who are not necessarily my students studying with me, then as a matter of fact, when you are running your normal CDF command, your calculator is actually strong enough to do the following. And you will understand what I mean when I'm pulling out that normal CDF command. Let's go second variables. I am navigating down to normal CDF. So now what I'm about to say now is that this normal CDF is actually strong enough to handle directly even if you are on the general normal distribution. Meaning, now for public viewers out there, if your instructor doesn't require you to go through the z-score steps, then right from here, where you are immediately on the general normal distribution bell curve, you can already execute your normal CDF command as following. Notice again, before I'm taking off from this screen right here, that's our general normal distribution here has mean at 3 and standard deviation 0.25. So with your normal CDF command ready for action here, and as I said, if you are not required to find the z-scores, then you can directly enter 2.9 for the lower end of your interval, and you can enter directly 3.15 for the upper end of your interval. But then make sure to adjust your center of the bell curve here to 3, because that's what the center of your bell curve of our current example is. And then our standard deviation here on this specific bell curve is a 0.25. And now we are ready for executing the command. And that command will give the quite close enough calculation. So the answer is expected to be the same pretty much. And that is the reason why we have this answer right here. So students of mine may ask me, why do I ask my own students to go through the process to find z-score? Because they are, even though we are allowed to use the TI the pretty strong and powerful technology, but I want to maintain your skill in understanding the z-score for the later learning in the quarter, and who knows, for your future courses, that maybe after this course you are going to have some good passion and move on to a more advanced course. Then z-score will be intensively used at your later courses. So forgive me if I'm asking you to go in a longer route compared to public viewers who learn from this lesson. But for my students in specifically, I am requiring that you have to go through the process to convert any of these values into a z-score. So students in my class are required to rewrite this problem as the problem where we're finding z-score between negative 0.4 and 0.6, and the answer would be the same. And so now we are ready for a final generalization here. Now let's start out with any general normal distribution bell curve with mean at mu and sigma, some sigma value. And the random variable here is x. And let's say we are asked to find the probability that on this general normal distribution bell curve we find our random variable x taking value anywhere between a low a and a high value b. Or in other words, we have an interval. We have an interval in anywhere on a bell curve, an interval from a to b. And so, of course, this interval has an area shaded between that, and that's what represents our probability equation. And so the generalization for my students that I am teaching is that I would like my students to use this method. From where our lower end of the interval, we are going to subtract the mean and divide it by the standard deviation. That will give us z-score for our lower end of the interval, and that's what my ZA is for. I am going to repeat again, but for the upper value of the interval, the value minus the mean divided by the standard deviation sigma, and that will calculate for us the z-score of our upper value, z-score of b. And once we have found the z-score correspondingly for these two low and high of our interval, then think about the standard normal distribution, where center now is at 0 and sigma 1. Then that lower end is equivalent or corresponding to z-score ZA that we have found previously. And that upper end right here is equivalent to the z-score Z sub b on our standard normal distribution. And this answer that we're looking for now is exactly the same as the answer that on this standard normal distribution bell curve. We're finding the probability where our z-score falls anywhere from the low z of a and to the high z-score of b. And the shading area, the two shading areas on the two pictures here are supposed to be exactly equal amount. And that's the method I would like my students to follow through. Even though, again, as I said, for public viewers who are not directly studying with me, then you can just use your normal CDF command immediately from here. Run your normal CDF with low at A, comma, with high at B for your interval, and with your mean enter, and with your sigma value indicated here, and run your normal CDF command right out from your general normal distribution bell curve. You should end up with your answer for this. But for my students, I require you to go one step extra. Find the z-score for each of these values correspondingly. Then we are going to execute the normal CDF command, entering the low z-score, then entering the higher z-score, then default the mean at 0 and standard deviation at 1. And again, as I said earlier, the reason I'm asking my student to follow this because I would like to maintain the understanding about z-score for my students, because maybe this class is the only class you have to take, but you will never know that after the class here, somebody may find some good passion for statistics and would like to go further. Then when you get to a higher course in statistics, then having a good mastery of your z-score understanding will be a huge bonus for your stats understanding.